Welcome to a code report solution video. In this video, we're going to be covering the solution to the problem entitled Chef and Magical Jars from the CodeChef February 2019 long challenge. The problem statement is very long, so I'm going to summarize the first three paragraphs and then read through the remainder. So basically, Chef is going to have N junior chefs, and they're going to each have a dish that they need to prepare. And if a dish requires X ingredients, that means it's going to need X jars, but Chef only has a limited number of jars, and he doesn't really tell the chefs in what order to go and get the jars, so it's going to happen sporadically. So starting from here, we know that there are N junior chefs numbered 1 through N, and for each valid I, the number of ingredients required for the dish of the ith chef is AI. And if there are J jars, then formally the following process happens. First, the junior chef takes some jars. Let's denote the number of jars taken by the ith chef by AI. Any distributions of jars such that each of the AI is greater than or equal to 0 for each of the valid i's, and the sum of those values is equal to j is possible. That's confusing, and I'll deconstruct it when we look at the examples. At any time, if AI is less than AI for each chef I that has not prepared their dish yet, the cooking session is a failure. Note that when it says each, really what it means is every. So if at any point no chef is able to complete their dish, the cooking session is a failure, and that means that we don't have enough jars. Otherwise, one of the chefs who has the at least as many jars as the number of required ingredients prepares their dish and returns their jars to the kitchen. Whenever some jars are returned to the kitchen, they are immediately taken by some other chefs that have not prepared their dishes yet, possibly all the jars by one chef. This process continues with chefs taking jars, cooking their dishes, and returning jars until no chef can cook their dish anymore, or all chefs have cooked their dishes. When all junior chefs have successfully cooked their dishes, the cooking session ends successfully. Chef wants to know the minimum number of magical jars that should be present in the kitchen initially so that the session should be successful regardless of how the junior chefs pick up their jars. Chef is a legendary cook, but he's not good at mathematics, so he asks you to help find that number. So probably out of all the 160 plus videos I've made so far, this is the worst problem statement I've covered, because it's so confusing, and it's actually a pretty simple problem. So let's take a look at the examples, and I'll try and talk through what this problem is actually asking. So here are two examples, and part of why this problem is also so bad is that the test cases provided, these examples, are really bad as well, and they don't illustrate what you actually need to do. So we have two test cases. The first one, we have 4 chefs that require 1 jar or 1 ingredient for each of their dishes. And for the second example, we have 2 chefs, one that requires 1 ingredient and one that requires 4 ingredients. So each chef needs at least as many jars as ingredients that they require. And the answer for these two are 1 and 4. And it provides an explanation for the first case, but not for the second. And it says for the first case, one of the junior chefs always picks up the only jar, cooks their dish, and returns the jar back to the kitchen. Then another junior chef picks up the jar, cooks their dish, and returns the jar. This procedure can be repeated by each junior chef so that they can cook their recipes. So what's not explicitly clear in this explanation is that there's sort of an evaluation that happens when all of the jars are picked up. So regardless of the order, basically what happens is the chefs are going to go and clamor for the jars. Once they're all picked up, we evaluate, is any chef able to complete their dish, which means do they have at least as many jars as they have ingredients. As long as every time this evaluation takes place, we're having successful sessions. But if at some point there's no chef that has enough jars, so basically enough jars to equal the ingredients that they require, then the whole thing's a failure. So when we have 4 chefs that each only require 1 jar, regardless of who picks it up, when they pick up the 1 jar, they'll be able to complete their dish. Then they put it back. The same thing happens again. The other 3 clamor for it. One of them's going to get it. And this is going to happen 4 times, but every single evaluation point where all the jars have been collected, at least 1 chef is going to be able to complete their dish, so it'll be a success. For the second example, which isn't explained, but I can explain it here, the answer is 4, and that's because if there's less than 4 jars, and the second chef goes to pick up the jars and gets there first, and sort of, if we skip back to this where it says, any distribution is valid such that AI is greater than or equal to 0, and the sum of these AIs is equal to j. That's basically just saying as long as all of the jars are distributed, it's valid. It doesn't matter who they go to, though. So if we were to have 3 jars for the second example, the second chef could go take all 3 of them, and then the first chef wouldn't get any. But if there was 10 chefs, the other 8 wouldn't get any either. But this chef wouldn't be able to complete his dish with only 3 jars. So it would be a failure. So we know, just by looking at the second example, that we need at least j jars where j is equal to the maximum element in our array of ingredients for each of our chefs. So we know at least that's going to be the minimum, our minimum requirement. But there are certain cases where we might need more of those, and these test cases don't really do a good job of illustrating that, but I'll show you 2 cases that do. So here are the 2 other examples. You can see for each of them we have 4 chefs. For the first example, the 4 chefs require 1 ingredient, 2 ingredients, 3 ingredients, and 4 ingredients respectively. And for the second example, each of the 4 chefs require 5 ingredients. And the answer for each of these are going to be 7 and 17 respectively. And the way we can reach these answers is by restating the problem and asking ourselves, what's the maximum number of jars that we can distribute to the chefs in the worst case possible, such that all of them get the maximum jars that they can get, but still not complete their dish. And the answer to that is by basically giving each of them AI minus 1 of their dishes, of their jars or ingredients. So for the first example, we would give the first chef 0, the second chef 1, the third chef 2, and the fourth chef 3. And for our second test case, we would give each of the 4 chefs 4 jars. So they would be missing 1 jar in order to complete their ingredient. And that would give us sort of the values 6 and 16. And we can state this mathematically by taking the sum of each of the elements in our array and subtracting 1 from each of those elements. And we can restate this by taking the constant out of our summation and multiplying it by n, which gives us the sum of each of our elements minus n. But this gives us the maximum number of jars we could distribute and have all of the chefs not be able to complete their dish. But we want to have the minimum jars that we're guaranteed that they'll be able to complete. So all we have to do is add 1 to this value here. And once we calculate that, we have our answer. And we know that in subsequent, so if we take a look at our second example, in the first case, we have 17. So each of them are going to get 4, except for 1 chef that we know will at least get 5. And then when he returns those 5 jars, even if 1 chef takes all 5 of them, they're going to have more than enough. And we know that for subsequent evaluations of checking to see is any chef that hasn't completed their dish yet that will have enough jars, even if 1 chef took all of them. So yeah, it's a very confusingly stated problem with really bad test cases and no explanation on the second test case. But once you figure out what the question is asking, which took me a while, it's actually really, really easy to solve. You basically just need to sum all the elements and subtract n, add 1 to it, and output that number. So let's take a look at the code for that. So here's our C++ solution. You can see we're reading in T for our T test cases, then looping through each of our test case, reading in N, the number of chefs, initializing value, which is going to be a long called answer, and then we're going to loop through each of the values of the ingredients that each of the chefs require, read this into a local called x, plus equal that to our answer, and then once we finish this, output the answer minus n plus 1, and you're done. And the last thing to talk about for this problem is going to be the time complexity, which for this problem is going to be big O of t times n, whereas t is the number of test cases and n is the number of chefs. As always, if you enjoyed this video and found it helpful, hit that like button. If you want to see more, make sure to hit that subscribe button. You can follow me on Twitter for reminders 30 minutes before contests start, and you can find all of the code shown in my videos on my GitHub page. Thanks for watching, and I'll see you in the next video.